to the optimized level. That is should be the right word for that. I want to give that material and the properties wherever it is needed, I give that. If it is not needed, I don't give that. And that is necessary. If you have seen honeycomb structure, it is basically also a lightweight structure because the material is utilized exactly at the place where the stress is coming. And that is what we are doing here in worm forming. We are creating high strength only in that upper region. Same thing we could do also in other beam structures. So this is, as you said, like this is basically the area where you have high hardness on the top. Then there is a transition zone of 20 millimeter, and the bottom part has basically low hardness, high ductility. In fact, this gives better crash than having complete B-beam of high strength steel or high strength properties. So you can see here the picture that what we are doing it here in this region, we are cooling it, and we are in this region, we are heating it, and in this region we are cooling at the less rate. The water content which is flowing in the die is much lesser, and that's why you can see that here the same temperature difference, if you can see at some particular time, here it is still 500 degrees centigrade, where here it has reached 20 to 40 degrees centigrade. So fast cooling, and other areas hardly cooled anything. And this is the advantage of soft zone technology, very much used in automobile technology. So basically, after your press hardening methodology, the second advancement of press hardening technology is soft zone technology. I would say practically no automobile part I have seen nowadays which does not have this soft zone technology. In fact, soft zone technology is the most important thing, and that makes the tooling difficult, but at the same time the crash more better. Now, as I told you, our lecture is optimization of material to highest extent. We don't want to give a single gram of material where it is not needed. And this is done basically on the side panel. You can see this side panel, side panel, side panel. Normally, if I would be 30 years back, I would have a same material, 1.2 millimeter, or maybe 1.5 material, based on the highest material which I needed. So example, I here need 1.9, I have complete of 1.9 millimeter material. Then came the thing, tailor welded blank. Tailor welded blank was basically something like 30 years old technology, where you join the different sheet thickness by a laser welding. And you can give a different thickness. And then you can give different kinds of material, strength. Even you can join different kinds of material also. So basically, then the second thing came from 1.9, I could say here I need 1.3, here I need 1 millimeter, in between 1.5. The part was optimized. And now come the second thing. I'm doing the worm forming. I'm getting the higher strength. Plus, additionally, I'm using the soft zone. So giving much higher strength, much higher ductility. Now, sometimes there is a limitation to the part. I cannot have so many welding zones everywhere to make a very complicated tailor welded blank. So what you do? You add a patch of the material to compensate even that small additional stretch which is coming. So you have these patches which are placed on it. They are just attached by adhesive or clip. So now we have advantage of how much? Different kinds of thickness, different kinds of steel property as a tailor welded blank, worm forming advantage, soft zone technology plus patch steel. We are coming closer to material utilization. We don't want to give single gram of material where it is not needed. We'll see in these lectures or future lectures that only by doing these techniques, we can come to a very optimum actually things. It takes basically more efforts, but finally every gram of material plays important role. How much it makes important role, frankly speaking. 1 gram, if you could reduce it, I could give 1 kilometer more to my electric car. Normally the batteries which you have in electric car, normally having say 500 kilometer range. it is as much kilometer equal to as much kilogram. 500 kilometer range, your battery size is 500 kilogram. So every kilogram I reduce is, I increase the battery, I compensate the battery, and I can say kilometer I'm getting more and more. So that is very important, and this would be practically, by doing it, we are saving around more than 20 to 30 kilogram by this process. It would be foolishness to use 1.9 kilogram of steel all the way. No? So this is also the process, as I told you, for the soft zone technology. We are putting the ceramic block in the area where we don't want any heating to be done. The ceramic blocks the convection of the heat. The part will not be heated. The part will be soft. So you can see the high zone area. This is the high zone area, and this is the soft zone area, and this is the transition area of around 20 millimeter. Plus, this soft zone technology has a very important use also on the flange sides. What happens normally if you have a very hard part, and in automobile industry, practically lot of joining is happen, I would say 70 to 80% joining is happened by spot welding. That is the most economical process. If there is no economical benefit, automobile will not accept it. How interesting it is, forget it. No one will do it. So economic benefit, spot welding, no one can beat that. Now if I am having a spot welding, I have to give basically first the clamping force, I have to give the current, holding time, releasing it. Now your flange is extremely hard by press hardening, 1000 to 1200 MPa. And just imagine how much clamping force it will need to bend this part to mate it with other part. Practically your spot welding tool will break. Now even if your spot welding tool is very, very robust, the part will break because you are giving so much high clamping force to bring that part. Plus additionally, if you are hitting the part to soft zone, to welding zone and cooling it, we are creating local heat affected zone. It means there is always chance of cracking that area. So always when you go for high strength steel, the first question you should ask, is it weldable or not? Because the problem occurs in welding. Now here I know that the best solution for my car is hot forming. So I have to find some solution also for the weldability. And that is the soft zone technology. We purposely make the area of the flange which is connected, suppose this is the roof area, that flange will be made softer by again the soft zone technology. Otherwise that area will break, the leakage will come, water will leak, and the part is basically not feasible. So without this soft zone technology, sometimes it is not possible to make the car. So you can see that what is done basically in this area, we are not allowing the heat to go to oxidizing temperature, and that's why we can easily basically do the spot welding of the part. So basically just what I said, initially we had this part, all different parts together. Like this part example I told you, 1 part, 2 part, 3 part, 4 part of different thickness one can make, but I have to make 4 parts. 4 parts, 4 toolings, joining, everything, problem. So let's make it 1 part, but 1 part thickness would be determined by highest thickness, not feasible. So this was the earlier approach, all 4 parts of different thickness. This here's warm forming, fine, but still 4 toolings. Now what people do, make this complete side panel, 1 single part, tailor welded plank, warm forming, soft zone, 20% mass saving, and better crash worthiness. This is the future. This is actually not future, this is done everywhere. Try to combine the parts. So the toolings are less, because as higher strength you go, the welding is a problem. Try to avoid the welding as much as possible. Again on this part, like which we know that, like our typical conventional part with so many different toolings. Some part is warm forming, majority of the part conventional forming, because this complex part is so difficult to produce at room temperature, impossible practically. The deep drawing of more than 150 millimeter is very difficult to produce this part. But I could do this part completely as a warm forming in some of the design, and then this part has a better crash worthiness than these 5 parts together. So the next tendency of lightweight technology is to see how can I combine the parts and make as a single part. It is not an easy approach because we have to also look from the lot of perspective because of the other areas which is has to be covered. But the whole thing is one has to start from the beginning approach that I have to combine the parts and see to it that I have less tooling, less joining methods. This is very, very important. So lightweight technology only does not has lightweight materials or high strength material. The approach begins much, much before that. This is a typical B-beam. Normally people talk B-beam as an interior part, but really B-beam has so many different components. The inside beam, the middle beam, and the outside beam. Practically all the 3 together give that crash worthiness. Plus additional structural parts in between. Now what I do here, 3 parts here joined with the warm forming and the soft zone part. Here I am using the patches on the basically B forming. So this part can also go to the one part with additional advantage. Again warm forming, soft zone technology plus patches, and then get one part instead of 3 parts. So this is very, very important that how you can get that warm forming. So basically I would say as we started earlier, we are using conventional forming. 50 years back, people were only using DC04 material, low alloy steel, because they found that it is sufficient. There is no requirement of that 5-star crash. There is no requirement of our carbon emission and no requirement finally coming, then why should I spend so much of money? Then the started coming is DP steel, trip steel, dual phase trip steel. That is the second started. People realize, yeah, it's good, I'm saving material, but the problem occurs of spring back. Problem becomes the wear of the tooling is very high. I have to repair the tooling very much, additional cost. I cannot get that high productivity. Then came the warm forming using this 22 Mn B5 material, and they realized that it is much easier. I can get very complex part. I can combine the parts very well. Plus I can give additional advantage that I can combine with tailor welded blank and patch steel. And it was giving me around 25% weight reduction. So that is more or less the state of technology up till now. Now in the future, as I heard also from ArcelorMittal, advanced high-strength steel is coming. And if they would find the solution to the welding problem, then it might replace the warm forming. Because the warm forming is the only disadvantage is the CO2 requirement because you are giving temperature. And using the same temperature again to cool it. You have to heat it and cool it. You are giving enormous amount of energy. And when you're talking about the life cycle of the car, finally that energy which you put in your car is equivalent to CO2. Your CO2 balance will go back. So that is one of the disadvantages of this warm forming. Advanced high-strength steel will not have that. So I believe that advanced high-strength steel is going to come in future, but slowly.